And then they see cyanide, so they say cyano. But this is the thiocyanate ion. And then you change your final E to an O. We went through all these rules. And then it's iron. And it's dark, dark red. So what I want you to do for part of the iron test, this is your original test tube. It's so dark you can't see through it. Then you take 1 drop of this and put it into a clean test tube. Then you put 2 drops of the ammonium thiocyanate reagent and 7 drops of water. You've diluted it by a factor of what? 10. That means it should look like a trace color. So I'm going to see both those test tubes. So I can tell you whether I think it looks like a trace color when you do it. Because the major problem with iron, if you don't clean your test tubes thoroughly, you're going to get, and almost everybody gets some iron contamination, but it's a very light red-brown. This you can't see through. This you can see through somewhat. Okay? So I can comment about it when I see it, say whether you got enough here or not. And the reason you add the extra 2 drops is to keep the equilibrium shifted towards this thing. Dilute things out, they start breaking down just because of the equilibrium shifting it back towards the reactant side. You reduce the concentration of the thiocyanate. Okay? So I want to see both of these test tubes when you come up, and usually that's the big delay. People come up with their test tubes, they want to take their quiz, they want to get their unknown and get started, and I make them go back to the locker and prepare the dilution. Then I always say, well, half the time I say, this should be a little bit darker because most people don't get it dark enough. I don't know why. Possibly because they lost some of their iron coming through. So I comment about that. So I want to see both those test tubes. And you're doing the original solution and a 10-fold dilution. Those are the 2 tubes you show me for iron. And I forgot to write the reagent here, so I'll write it here. Because right here I'm going to do my cobalt test. This is my iron test. Here's my cobalt test. This is procedure 18. Whoops. You're adding what? Ammonium thiocyanate again. And you say, no, that can't work. Yes?
Back to the iron.
Yes.
Are we not, for the iron 3, is that not present at all?
There's some of it that does form a complex just like this, except it's not as dark a color.
But it is, that iron is included in the group 3A, right? It's both.
Yeah, both.
Iron
In other
2
words, I
and-
said whenever you have iron 2, you're going to have iron 3. You can't avoid it. Even
Okay.
here, when you've reduced it, you'll get mostly this, but there'll be appreciable amount of this.
Okay.
And I think the iron 2 is more intensely colored than the iron 3. And by the way, that's, you notice this, when the Petrucci book talked about it, he used the formula FeSCN4. And that's because as you dilute the thiocyanate, let me write the equilibrium here. SCN minus. There's the equilibrium. As you dilute it here with the drops of water, it'll shift this way and break down more, and you get a lighter color. So the reason for adding the 2 extra drops of thiocyanate is to shift it this way. Okay? So that's why I had you add 2 drops of thiocyanate. And sometimes if you don't see a really dark color, you can add another drop of thiocyanate because the factor between 11 drops and 10 drops is not significant. And not having enough thiocyanate, shifting it all the way to the fully complex ion could be a problem. Okay? And this will make it lighter. And that was, remember when I was talking about the formation of the complex is going in a series of steps. The 4 is the one your book put down, but if you add enough extra thiocyanate, it goes to the hexes. Now, the other thing I was going to point out here, further down in the notes, he gives you an alternate test for making a precipitate. We're not going to do that, so don't try to make the precipitate for me. In other words, he describes what happens if you add, he says put potassium hexathiocyanate, dark blue precipitate. In other words, you're doing the redox reaction and making a precipitate between iron and the hexathiocyanatoferrate, okay? So don't worry about that. People always try to make that precipitate. Mr. Cunningham, when he used to teach the class, always had the people make that precipitate because he liked the precipitation test better than the complex ion color. I'm happy with the complex ion color. And you can distinguish between, when you're doing your unknown, if this is a principle of iron, it's going to be so dark you can't see through it. If it's a medium of iron, it's going to be so dark you can't see through it. If you do the dilution test, and if it turns out this dark still, it means you started with what? The principal. If it turns out lighter, then it means you started with the medium. So you can't distinguish between the two colors for the principal and the medium from doing that first complex formation reaction. So what you're going to do is do the dilution on your unknown and then see how it matches up. If you don't have iron at all, or if you get to this stage and you get such a really light color precipitate that is much less than light than this diluted one, what's your conclusion going to be? Yeah, you don't have any. You have a contamination. Because remember, if you don't report a trace, you lose 2 points. If you have a contamination, you say it's a trace, you lose what? 4 points. Oh, statistics say, I'm not going to gamble if it's that light. You can, if you want, say, well, maybe I had a trace and I lost something. Especially, well, if you went through all the procedures and didn't find anything else, then you could say, I might have had iron in there, or I really messed up and I should get a new sample. People always ask me, how many ions do you put in there? And the answer is, think about the statistics. I said, I'm not going to give you any distilled water samples. I don't do that anymore. I used to get a lot of answers for distilled water with 3 or 4 different ions in there. Okay? So I don't do distilled water anymore. I figure if you find ions in distilled water, you're in trouble. So you'll have at least 1 at the low end. This one has 7 different ions, 7 at the high end. Chances are, somewhere between 4 and 7, you have the highest probability of how many ions you're going to have. Right? So somewhere in between 4 and 7, like 3 or 4, is a more likely thing. Same thing for procedure for experiment 2. There are 8 ions. I might have 1 sample with all 8 of them in, and I might have 1 sample with only 1. But most of my samples have between 3 and 5 or 3 and 6. Okay, so those are the things you want to think about. I don't tell you how many because each sample does have different numbers of ions. But there's none of them are going to have less than 1, and none of them are going to have more than 8 in experiment 2. Because 8 is the maximum number I can put in there. That's all the ions are. So same thing here. You're going to have some ions. And the most logical thing is I say I'm going to be halfway between the maximum and the minimum. Okay, so coming back to this one, here I did ammonium thiocyanate and I got this complex. In the other quarter of the solution, I did ammonium thiocyanate and I'm doing a cobalt test. What would you say should happen there? As soon as I add ammonium thiocyanate, you should get the dark red-brown precipitate. Why don't you? Well, before you do that, And actually, if you forget, you can do it afterwards. You're going to add sodium fluoride. Now the sodium fluoride is a white solid. You want to add a little bit of, on the tip of the spatula, you want to make a saturated solution of sodium fluoride. So you should have a little bit of solid. First you stir it up, then you centrifuge it, and you'll have a little bit of sodium fluoride solid left on the bottom. If you don't have any sodium fluoride left, add another little bit. You don't want to fill up your test tube with sodium fluoride. Then the other thing that happens here, sodium fluoride etches glass. That's why we have so many good, why we have so many counterbalance test tubes where the whole bottom of it is opaque, because people put a ton of sodium fluoride in there, and as it stands around, it etches the glass, and now you have to buy a test tube. So when you're doing that test, you might want to find one of my better looking old test tubes for the test. Okay. So first of all, you want to make a saturated solution of sodium fluoride. And then you want to add this is the old-fashioned way of abbreviating ethanol. Ethyl alcohol is the common name, and that's where the ECOH came. Ethyl, and then the OH for the alcohol. Now, the alcohol stabilizes the complex you get with cobalt. First of all, the sodium fluoride. And if Fe2 plus does this, I did 2 plus before, so I'll do 3 this time. Okay? So what you're doing is forming complex ions to remove the iron. That's why you want the saturated solution. Now sometimes people will discover that this solution is sort of a purple color. That means you didn't add quite enough fluoride. You can go back and add a little bit more fluoride, stir it up and centrifuge it. It'll remove some more of the iron. Because this thing is going to make thiocyanate. That part's spelled the same. And of course it doesn't make ferrite, it makes cobaltate too. Okay? And you don't have to worry about the cobalt-3 too much. And this is a blue solution. Now here, the color isn't as bad. If it's really dark blue, it's a principal. Medium blue, medium. And light blue, a trace. And cobalt is not a common contaminant such as the iron, so you won't have a problem with that. So this is not a bad, this one, and by the way, people say, can I dilute it? The problem is I don't put alcohol out there for you to dilute it with, and chances are the medium blue, if you diluted it, would already be almost an invisible blue. But there is enough of a color gradation that you can tell whether you're getting really dark, and I'll comment about your blue color when you bring it up, just to see how close you are to what it should look like. Now you won't have anything to show me for, you will have something to show me for nickel. What I said is you're going to calculate the drops by dividing by 4. Now we're going to procedure 19 here. Okay. You want to first of all make sure it's basic. This is the nickel test. Now, if you had a lot of iron in your sample, this is going to make a precipitate with the iron. You want to remove the precipitate because it's going to be a reddish-brown colored precipitate or greenish colored precipitate. But the point is it's going to interfere with the precipitate you're going to try to make with the nickel. So if you make a precipitate, when you make it basic with ammonia, remove the precipitate. So I'll do this little thing right here. And then it's going to make the complex with nickel. Then you're going to add dimethylglyoxine. There's the dimethyl part. Whoops. Yeah. Okay. Now this is dimethylglyoxine. It's acidic, and when you add NH3, it's going to make it's going to make that ion, which is abbreviated HDMG minus. It's going to pull one of these hydrogens off and makes the negative ion. So that's what the ammonia does there. And then this forms whoops, the end's sorry. Whoops, I got too many C's. In other words, it makes a chelate with the nickel. And there's another one, so that's why it has two of them. And so you're making, and people always give me all the carbons, hydrogen, nitrogen, there's nothing wrong with that. But I'm going to abbreviate it. You're making this thing. It's a strawberry red precipitate. Book has a lot of fruit colors in here. So it's a strawberry red precipitate. It's bright red. Usually what happens if people don't make this basic, they see red around the top of the test tube and on the glass, but they don't see red in the solution. Or if they see a red color solution, that's not the test for nickel. It has to be a precipitate. I'll underline it. It's a precipitate. Again, you can get some impurities that will give you a red color with the solution with the dimethylglyoxine, but only nickel will give you the precipitate. You have to get a precipitate. And what's the name of that precipitate? Remember good old this? I think we named this a long time ago. Notice it's not an ion because there's no charge up here. Okay, so it forms a chelate that's specific for nickel. And the red, if you get a red solution, it doesn't mean you have nickel. It has to be a precipitate. You can add a little bit more ammonia because sometimes what you're seeing is the reddish color around the top of the test tube where it's not basic and the precipitate should be forming. So when you add some more ammonia, the precipitate does form. Okay. Then the manganese test, next procedure. Fourth part, you dilute it with water. You add 3 molar nitric acid, make sure it's acidic, and then you're adding sodium bismuthate. It's another solid, so it says a few grains. In other words, a little bit on the tip of the spatula. Again, you want to form a saturated solution. Sodium bismuthate. Somewhere it has that. In the acidic solution, by the way, the sodium bismuthate goes to bismuthic acid. Okay. That's the thing that he actually puts in the net ionic equation here. It's on the middle of page 216. The manganese ion plus the bismuthate ion gives you the permanganate. This equation looks fine. And you get bismuth ion left over. So this plus manganese gives you the permanganate. And this is the most difficult one because, again, it's like iron. The principal is so dark you can't see through it. The medium is so dark you can't see through it. They'll be about the color of the permanganate solutions you used in kinetics. And unfortunately, you can't dilute this out because as soon as you start adding water to it, what does it do to the permanganate ion? It decomposes it. And so the color disappears, not because you're diluting it, but because you're decomposing the permanganate ion. Now, one of the things you can do, if you don't see the violet color appear when you mix these reagents, you put it in the boiling water bath for a few minutes, because way back here, when you're adding all this hydrogen peroxide, it says to boil a bit before you move on. It's to decompose hydrogen peroxide. If you don't decompose the hydrogen peroxide, it's going to prevent the permanganate from forming. That's why you don't just want to throw a ton of hydrogen peroxide in back of these other procedures. That you put too much in there, it won't decompose, and it'll prevent the formation of the permanganate ion. So the trick is to add just the right amount. Here you're using the color to decide. Here you're adding a drop. If precipitate dissolves, you add another drop. When the precipitate doesn't dissolve, you separate it, test it again by itself. If it doesn't dissolve, you haven't added much extra hydrogen peroxide, and then you just boil again. Notice wherever it says boil gently for a minute or two, it's usually to decompose the hydrogen peroxide. And it means you're holding the casserole way above the flame and it's just barely bubbling in your casserole. You don't want to evaporate everything away, which is the most common thing people are bringing up for me to see. Okay? So I'm going to stop here. I'll finish up the B part of the group the next time. And I guess it's time for a quiz.